Good morning, everyone, and welcome to projectile motion. So yesterday we talked a little bit about the components of projectile motion. Today what I'd like to do is go through a couple of examples and hopefully kind of tie together what you did for homework last night and get you started on some problems. So make sure you have your journals out and let's take a look at some projectile motion. To start off, what I'd like to do first is let's just review a little bit about projectile motion. And so let's just take a look at this diagram. And so if you'll follow along with me here, this is representing a projectile motion problem. And this hopefully looks familiar to you because this came from the Physics Classroom online tutorial. And overall, this just shows what's happening with vectors as time goes on. And so hopefully this is something that you copy down in your journal. But if not, let's just follow along with me here. There's a couple of things that you should notice offhand. And the first is that let's look at this horizontal velocity here. So notice this horizontal velocity vector. So this vector, as time goes on, and we're assuming that each position here is following 1 second after another second. And so as time goes on, one of the things that you should note is that our v, I'm going to use an h here to represent the horizontal velocity, is equal to a constant. And that's because horizontally, when you fire a projectile, we're assuming no air resistance. And so with no air resistance, the horizontal component of the velocity should remain constant. And so in this example problem, a cannon is firing a cannonball, and it leaves the cannon up here at a velocity of 20 meters per second. As time goes on, the horizontal component stays constant at 20 meters per second. But what we notice, though, vertically is happening is the vertical velocity is continuing to increase. And so they're using the actual values of acceleration here for velocity. But you notice that after 1 second, so I'm going to say that this is 1 second here, the velocity is about 10 meters per second. After 2 seconds, the velocity is about 20 meters per second. After 3 seconds, the velocity goes up to 30 meters per second. And after 4 seconds, the vertical velocity is 40, and then as you can guess, here at 5 seconds, the vertical velocity gets to be 50 meters per second. So what we know is, and you should write this down, that the vertical velocity vector is equal to the acceleration of gravity, which is g, times the time to fall. So in this case, you can see over here after 4 seconds, we could take 4 times 10, or 9.8 is what they did here, we get a vertical velocity of about 40 meters per second. And so that's the equation used for the vertical velocity component. So that's why at the beginning, at time equals 0, there's no vertical velocity. But after it starts going, we get that. And so what this is showing is that if you go and combine all of these, we're getting what's called a parabolic path. And so this parabolic path is showing the actual path of the projectile as it goes through the air. So the last thing I'd like to do here, I know my diagram's getting a little bit messy, but what I'd like to do is actually go and create and show the vector addition of these two vectors. So I'm going to do that over here at the 3 second mark, just because we've got a little bit more room here. So at the 3 second mark, and this is what happened on the back side of your paper for your homework last night, is they showed what was called the parallelogram method. And so they went along and they just created a parallelogram or a rectangle. And when we add the components together, you should get something kind of like this. Whoa, I don't know what just happened there. Let's try that again. Something kind of weird happened. Let's see, so I don't know. Well, ignore that squiggly line there. But what we got here is a vector that's going something like that. And so if I were to do that for each of these, you can see that when I added this vector together, I'd have a vector like that. When I add these two vectors together, it'd be something like that. This one, when I add it together, is going to be something kind of, oops, kind of like that, although this one should have gone a little bit longer. And when I add this one together, the resulting vector is something kind of like that. So the important thing to note is that as time goes on, you notice that our resultant vector, the green vector, is getting more and more vertical. So this is my resultant. And it's getting more and more vertical because this vertical velocity vector keeps getting bigger and bigger and bigger. The horizontal is staying constant, the vertical is increasing, so it's getting bigger. Let's look at something a little bit different. Let's imagine that you're sitting here, this is you, and you've got this red ball that you've got on the table. And so what you decide to do is you decide to push it along the table. And so you can do this just with a friend of yours if you'd like. So you push it along the table, you give it this horizontal velocity. Now a friend of yours is standing over on the side, and they've got this green ball. And what their plan is they'd like to drop this ball as soon as yours gets to the edge of the table. So yours is going to go along, and as soon as it gets here, your friend, in case you're not sure, we'll just label this here. That's your friend. So what they're going to do is they're going to drop it. So your ball, as it goes along, is going to follow a parabolic path. Theirs, as it drops, is going to just go straight down. So the interesting thing is, let's take a look at yours after 1 second. So yours after 1 second probably going to be about here. Maybe another second later is here. And let's just say a third second, you hit the ground. Your friend's ball, what you'll see is that after 1 second it's going to be here. After 2 seconds it's going to be here. And then after 3 seconds it's also going to hit the ground. And so this vertical distance that they both fall is going to be equal. And so that's a key point with projectile motion, is that the horizontal component and the vertical components are separate. And so for both of these, your friends that's going to fall, the vertical velocity is just like we said before. It's the acceleration of gravity times time. And that goes for yours that you rolled off the table and theirs that they dropped. So in this case, when they drop them, they're both going to hit at the same time. And so, you should try this and push the ball off the table, have your friend drop another ball right as soon as they see yours, and they should both hit the ground at the same time, because vertically, the reason they're both falling is because they both have the acceleration due to gravity. And what we said is that if we drew a free body diagram of any projectile, it's just going to look like this. And it's going to have the one force vector going down, and this is going to be the force due to gravity. In other words, its weight. So that's why when you roll your ball off the table, it will have some horizontal velocity, which is what's going to determine how far over it goes. This is its horizontal velocity. And so if we wanted to find this distance, that distance is just going to be the horizontal velocity times the time. And so what ties everything together here is the time. And so vertically, they all accelerate because of this weight. And it's the acceleration due to gravity with g equal to approximately, we'll just use 10 meters per second squared. Okay? So let's go and take a look at an example just to tie this all together. So let's just draw this out again. And so for an object that's falling, so if we've got, let's again just say that we've got a cliff or a tabletop, and let's just say that you roll something off up here, and so you give it this horizontal velocity that it starts with. We know that it's going to, so if we imagine that we've got the ground along here, it's going to follow some type of parabolic path like this as it falls. So if we want to figure out the time to fall, let's look at this equation. So let's just say that this is up some given distance. So I'll call this my distance to fall. Then our equation that ties a lot of this together is our time to fall equation. This is from our free fall, and it's equal to the square root of 2 times the distance to fall, all divided by the acceleration due to gravity. So that'll tell you how far you've got to fall if you know this distance. But let's just say that instead, what you wanted to figure out was, if we're going back to horizontal, say you wanted to find out, well, how far over will I land? Well, we said this horizontal velocity's got to be constant. So the distance horizontal is equal to the horizontal velocity times the time to fall. And what we call this is what's called the range. In other words, how far out horizontally will something go? So that's called the range. And that kind of sums up a few of the things that we've got. So let's go and do an actual practice problem. So let's just say that we've got someone who's, I don't know, on a longboard, and they're cruising along, and let's just say that they thought it would be fun to go off this dock or this jump or something and land in the water. But unfortunately, there's some rocks right here. And so these rocks go out approximately 5 meters. And we need to know, are they going to clear it? So let's just say that this distance here is, oh, what's a good number here? Let's just say that they're up pretty high. Let's say that they're up at 20 meters. I guess that's kind of a high dock. And let's say that they're moving along here with a horizontal velocity equal to 12 meters per second. So just horizontal. They're just launching off like that, so no angle, nothing like that. So we want to find out, will they actually clear these rocks that are out at 5 meters? So the first step we need to do is figure out, well, how much time is it going to take them to fall? So they've got 20 meters to fall. So why don't we pause the video, work with your neighbor, and see what you can get. Okay, I'm assuming that you paused the video now. So let's take a look at this. So the first thing that I would do is figure out how much time does it take to fall. So our time to fall equation is equal to the square root of 2 times the distance to fall over the acceleration due to gravity. So in order to solve this, we're going to take 2 times 20 meters divided by 10 meters per second squared. And so 2 times 20 gives us 40, divided by 10 gives us 4. The square root of 4 tells us that the time to fall equals 2 seconds. They're going to drop. It's going to take 2 seconds for them to drop. And so they're going to be going on this path. We need to know, will they make it? So we know our time to fall is 2 seconds. So in order to find out, is their range greater than or less than 5 meters, we can go and use our horizontal range equation. So the horizontal distance is equal to our horizontal velocity times the time to fall. And so in this case, it's 12 meters per second times 2 seconds, and their horizontal distance comes out to be 24 meters. So they cleared this by a long shot, which is great. We don't want any skateboarders to be harmed in the making of this physics problem. Okay. So, what I would like you guys to do is your homework is to first study the projectile motion review sheet. Study projectile motion example sheet. And so that's got a couple of worked out examples and shows you how to do things. And what I'd like you to try is the PAT projectile problems, and just try numbers 1 and 2 for homework. So look at the example problems. If you notice on the projectile motion example sheet, there's a type 1, type 2, and type 3 problems. So see if you can first identify which type of projectile problem these are. So identify the type of problem and then give it a shot. And so I think after you study this sheet first, it should help you out so that when you do these two, it'll be good. And then when I come back, we'll go over the homework from the other day and take a look at that. So bring any questions you have to class. All right. Good luck and have a good day.